All right, electron configurations. Electron configurations. That second part right there that's up on the board. Because atoms of different elements have different number of electrons, a distinct electron configuration exists for each element. I said yesterday that these electron configurations are like fingerprints, okay? Oxygen has its own fingerprint, okay? Nitrogen has its own fingerprint. Now, are all nitrogens the same? Yeah, they have the same electron configuration, but it is a distinct configuration when you're looking at, say, nitrogen compared to oxygen. Why? Because if it's a neutral element, if it's not an ion, then they have different number of electrons. Now, look at your periodic table. The atomic number, which is, go ahead and find it. It's usually in the upper left-hand corner on our tables that we have. So let's look at nitrogen. The atomic number of nitrogen is 7. So, if nitrogen is a neutral element, it will have 7 protons and 7 electrons. Now, depending on what isotope you could have, it could have different number of neutrons, but if it's neutral, we're set on 7 protons, 7 electrons. Oxygen, right beside it, atomic number 8. 8 protons, 8 electrons. All right, so oxygen has 1 more electron than what nitrogen does. Okay, has 1 more proton too. Now, electrons are added to orbitals according to 3 basic rules. And these 3 rules are, first of all, Aufbau's principle. And that states that electron occupies the lowest energy orbital that can receive it. So, these orbitals are lined up. Remember that they're probable places that are around the nucleus. Okay? So these orbitals are probable places that electrons can be, and the electrons will fill those orbitals based on the lowest amount of energy. So the lowest energy ones are closest to the nucleus. Now, it would be fine and dandy if everything went in a distinct order. But that's the trouble with electron configurations. That's what makes them a little bit tougher, is that there are overlapping of different orbitals. As you can see here, the up arrow is the amount of energy. And if you look, here is the first principal energy level. Here's the second principal energy level. Here's the third. Notice that there is an overlapping between the third and the fourth energy level right here. So, it is less energy on the 4s orbitals than on the 3d orbitals. So there is overlapping. That's what makes these configurations a little bit tough. Now, what I've seen with folks is that these things, once you understand, once you get the pattern, then these things are very, very easy. But you got to wait till you get that aha moment with the pattern and say, oh man, this isn't that tough. This isn't that tough. So, Aufbau's principle states that an electron occupies the lowest energy level that can receive it. Pauli exclusion principle states that no 2 electrons in the same atom can have the same 4 sets of quantum numbers. We talked about the 4 quantum numbers yesterday. What Pauli exclusion's principle states is that no electrons can have the same 4. Now, they can have 3 out of the 4 the same. Okay, they can have 3 out of the 4 quantum numbers the same, but that fourth one they cannot have. So they will not have all four of the same quantum numbers. Okay? If you remember, okay, that we talked about a spin quantum number that said, hey, if you're on this orbital, 2 electrons per orbital, one spinning in clockwise, the other spinning in counterclockwise. So that could be the only difference. That 3 of the 4 quantum numbers are the same. They're just spinning, the electrons are spinning in different ways. Okay? So this is a picture I showed. And remember I said that the box is an orbital. The box represents an orbital. The arrows represent electrons. So hydrogen, okay, hydrogen has the first energy level, okay, the S sublevel. So we know the shape is round because we know that sublevel is round. And its spin is, let's say, clockwise. So then, helium would have 3 out of the 4 same. Same principal energy level, same sublevel, same sphere of the sublevel. It's just now that its spin is the opposite that the hydrogen was spinning. Okay, so 3 of the 4 quantum numbers were the same, but that fourth one, the spin quantum number, was different. Hund's rule. Hund's rule states that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second. Okay? Now, if we look, we remember, if you remember yesterday, here is nitrogen. Okay? We stated that nitrogen earlier today has 7 electrons. All right? Now, what we mean by Hund's rule here, 1s, 2s. Those are both different orbitals, but if you look, we said that there are 3 p orbitals. So 3 times 2 is 6. So the p orbitals can hold a possible 6 electrons. Remember, we labeled this px, py, and pz. Okay? So of those 3 different orbitals, when we are filling them, we have to have 1 electron in each orbital before we can double them up, based on Hund's rule. Okay? So if I show you this little picture here, here's nitrogen again. Okay? Here's the s orbital. The 1s orbital is filled. The 2s orbital is filled. When we get to the p orbitals, we have 1, 2, 3 per orbital before we double them up. Now this bottom one, see how I have doubled up here, but I don't have any on that orbital? That is going against, that is violating Hund's rule. So I have to fill this orbital, or not fill it, I have to have an electron on this orbital before I can double any one of them up. Okay? Now, this is a very important diagram. And I have another one right behind it because this is going to help you with your electron configurations. Okay? Remember, we said yesterday that there is the s orbitals only have 1. Okay? So, if we have 1 orbital that can hold 2 electrons, the s orbitals have a possible 2 electrons. Well, look right here on your periodic table. Okay, on your periodic table, groups 1 and group 2 are the s orbitals. Okay, groups 1, groups 2 are the s orbitals. Now, you see where I'm doing the groups. You should have little numbers up here that says 1 and 2, somewhat similar to what I have there. So groups 1 and 2 are the s orbitals. Remember, we said that the p orbitals, there are 3 p orbitals, the px, py, pz. 3, excuse me, 3 times 2 is 6. Look at this blue block here. Okay? This blue block is the p orbital. If you count, starting right there with boron, carbon, nitrogen, oxygen, fluorine, neon. Okay? right there. Those 6 are p orbitals. Okay? Something to go back on. Okay? Something to go back on. Look at my periodic table up here. Okay? See that they put helium over here? Okay? Up there, up here on the board. Okay? Up here on the board, right here is helium. Helium's really in the S block. We'll understand later on why we put helium over on the right-hand side of the periodic table, but helium's an S block element. Okay, just something to remember. So, when I went to the P block, 1, 2, 3, 4, 5, 6 across there corresponding to the 6 electrons. Okay, the 6 electrons that the P orbitals can hold. Now, we said that the D has 5 orbitals. 5 times 2 is 10. Okay? Count across right here. My little green ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These right here are your D block, ladies and gentlemen. Now, with the D block, okay, with the D block, D is equal to N minus 1. Okay? D is equal to N minus 1. So if I look right here, here is my first group of Ds, correct? Well, what is N? These are the N's right here. So my first group of Ds are in the 4th period. Okay? So N is 4. What's N minus 1? What's 4 minus 1? 3. Okay? So these are really the 3 Ds. Okay? Right here. Here are Ds. N is 6. What's 6 minus 1? 5. So these are 5 Ds. Okay? Now, you remember when I showed you the slide and said there's overlapping that is occurring? Okay? Our first overlap, and if I, let me go back, 100 rule, let me go back here. Right here, our first overlap, 4s and 3d. So 4s fills up before the 3d orbital. Well, let's go back here. Okay? Right here, s is equal to n. So this is 4s right here, 4s. Then comes d. Well, d is equal to n minus 1, so this is 3d. That's that overlap. Okay? That's that overlap happening right there. Okay? Down here, the lanthanide and actinide series down at the bottom, the intertransitional elements. Okay? These are the F block. Remember, F has 7 orbitals. What's 7 times 2? 14. Do you think it's a coincidence that if I count across here that there are 14 there? Not a coincidence. Those are the F blocks. So, as I'm looking, S, P, D, then F. Those are where everything is at on the periodic table. If you want to label your periodic table, go ahead and do so. That's your periodic table to do what you want with it. Now, I'm just telling you that you may or may not be using your periodic table when we're dealing with these. I might give you one of my periodic tables to see what you know without it all colored up. Okay? Now, F is N minus 2. Now, remember that these F's fit in right here in the 6th and 7th period. So this top row of F block right here is N minus 2. Well, what's N? N is going to be 6. What's 6 minus 2? 4. Okay? So these are the 4F. Okay? These right here are the 5F. Because 7 minus 2 is 5. Okay? So, these quantum theories with the quantum numbers help explain the way that we arrange the periodic table. Okay? As I look at this, this is the one that I had on the video. Okay? we can see here that the orange right here are the S block. Okay? Here are the D blocks. Here's the P. And here at the bottom are the Fs. Okay? And you can see that all of the Ds are N minus 1. And all the Fs are N minus 2. Now, you'll have to do some of this stuff on your WebAssign later on. So we're going to go through. What these are these are just orbitals, okay? So, these are orbitals. I know, once again, an important thing to remember is S has 1 orbital, P has 3, D has 5, F has 7. Okay, so what this represents, the 1s orbital, main energy 1, main energy level 1, the S sublevel. The second one, main energy level 2, the P sublevel. And here are the 3, or excuse me, that's an S sublevel, I'm sorry. And here are the 3 P orbitals that are on main energy level 2. All right? Now, we know each orbital holds how many electrons? 2, right? So when I fill this up, I'm looking at oxygen here. How many electrons does oxygen have? How many electrons does oxygen have? 8, right? So I've got to put 8 electrons in these boxes. So how I'm going to do that is I'm just going to start by adding. Well, this is nice. Okay. This board has really been driving me crazy because it doesn't seem to line up very good, especially on my left-hand side. Okay. Let's see how we go here. That's better. So I have 1 electron. I have 2 electrons that I've added on, okay? And you might want to write this down if you don't have these down because you're going to need to do this again, okay? So I put my 2 electrons there. I can double them up because the s orbital only has, or the s sublevel is only the 1 orbital, okay? Now, I'm on the second. I have 2 electrons on my 2s orbital. So how many electrons do I have left? I have 4 electrons on there. How many do I have left? 4. Okay? I have 4 electrons left. So when I'm adding the P, I know that I have to have 1 electron in each one of the P's before I can double them up. So I go here, 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 and then finally I can put 2 in one box because I have 1 in every other one. So if you count my green arrows, 2, 4, 6, 7, 8, I have 8 electrons represented right there. I have 8 electrons represented. Now, let's look at silicon. Okay, find silicon. Si, how many electrons does silicon have? How many electrons does silicon have? 14, right? Now, let's look over here. Let's look back at my periodic table on the board, on the wall back here. Okay? See silicon's right here. Okay? See silicon right there? I know that this is in what block? What block is this? The P block, right? So this is 2 electrons on the P block. Okay? What energy level am I on? The 3rd one, right? So this is going to be the 3rd energy level. I'm going to have 2 P electrons on the 3rd energy level. Okay, look up here again. Here's the 1st energy level. These are the 1s's. Okay? Here's the 2s's. Here's the 2 P's. Here's the 3 S's. Here's the 3 P's. Okay? So when I'm adding 14 electrons for silicon, right? So I know I have an up and a down. I have an up and I have a down. Now here, remember, I've got to go up in every one of the P's before I can go down. How many electrons have I represented now? 2, 4, 6, 8, 10. Right? I'm counting right, correct? Now, s orbitals, fill up. Now I've got 12, 13, 14. So that is my ground state electron configuration. A ground state electron configuration. And this is just one way to represent an electron configuration. Now, when we start writing the actual electron configurations, okay, we're going to write stuff like up here on the board. 1s, and it looks like it's to the 2 power. 1s to the 2 power. Well, what does that represent? Well, in the red right here, the 1 is the energy level. So this is main energy level 1. This is the sublevel in the blue. The sublevel can be either S, P, D, or F. Okay? S, P, D, or F. And in the green up here, in the fluorescent green, we have the number of electrons in that sublevel. So this is telling me that I'm on the first energy level, I'm on the S sublevel, and there are 2 electrons on the S sublevel. Now, look at your periodic table. Okay? Find main energy level 1 up at the top. Okay? The S sublevel is the only sublevel on main energy level 1. Okay? There are 2 electrons on that S sublevel. So this right here, 1s2, is the electron configuration for what element? What element? Helium. Okay? That is the electron configuration for helium. Now, we're going to roll with these, okay, and make some electron configurations. Now, as I'm reading my periodic table, I read it just like a book. Left to right, left to right, left to right. All right? So, I look at copper. Okay? Point your finger to copper. What energy level is copper in? The 4th, right? Copper is also in the D block, right? All right. Now, just like reading a book, I start off at the very top of my periodic table. And here, let's look at this. Where's copper at? Copper is right here, correct? That's where copper is on my periodic table, right? So, as I'm making my electron configuration, I start up at the top here. I start with 1s2. Meaning that I have 2 electrons of the S sublevel in the first energy level. Okay? I read my book. 1s2. Come back to my left. What's next? 2s2. As I'm reading in my book, where do I come next? To p's. So what's next? 2p. I'm not going to separate them into x, y, and z. I'm just going to say 2p, 1, 2, 3, 4, 5, 6. 2p, 6. So right now, I'm right here where my little dot is. Do you understand that so far? Just reading the book, left to right. Okay? After my 2p's, I come down here to my 3 s's. So next is 3s2. After my 3 s's come my 3p's. I have 6 of them. 1, 2, 3, 4, 5, 6. So now I'm right here. What comes after 3p? 4s. So I'm at 4s2. Now here's the first big rub. Here's the first big rub because I'm now going into the D block, and D's are equal to n minus 1. Okay, so what is my n? My n here is 4. What's 4 minus 1? 3. So next come my 3 D's. Remember, that's the overlap. That's where the overlapping occurs. Now, I have 3D, and as I count, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 electrons on my 3D sublevel. 9 electrons on my 3D sublevel. So that right there, folks, is my electron configuration for copper. Now look, here's a check. Here's a quick check. How many electrons does copper have? 29, right? Now, if I add up all my little exponent numbers here, okay, that should equal 29. So I have 2 and 2 is 4, 4 and 6 is 10, 12, 18, 20, 20 plus 9 is 29. So there's a quick check you can do. If you add up all of your little exponents, it ought to equal the number of electrons. Okay? Now, let's go back. Okay, let's go back. Tantalum. Okay, find this on your periodic table. I don't know why I put that one in there. I'm not real. There we go. Okay, I'm seeing it right here. Okay, finding tantalum. It's element number 73. All right, element number 73. So, as I'm following my periodic table, follow along with me. Once again, in this, you're going to see is going to be redundant. I'm going to start off with 1s2. Then comes 2s2. 2p6. 3s2. 3p6. Where am I at right now? What number? What element am I at? Argon. Okay? The last one of the 3p's. Then comes 4s2. Remember, after the 4 s's come the 3d's. So I have 10 on the 3d's. And then I come back to the 4 P's as I'm reading my book. Because remember, P and S have the same as the energy level. It's not N minus 1. Okay? So I'm at 4P6. That would be element krypton. The element krypton right here. After 4P6 comes what? After 4P6 comes 5, what sublevel? S, and it can hold 2 electrons. After 5s comes the d orbital, but remember, d is n minus 1, right? So I have 4d10. And then comes 5p6. So now where am I at? What element? What element am I at now? Xenon. Okay. Questions for me yet? Any of it making sense? You seeing the patterns? Seeing the patterns? We're not finished with this guy yet. We got some more to do yet. What's after the 5p6? 6s2. Now, here's another one. Okay? Here's another one because I go from 57. Okay, 57 is a D, right? With me, see where I'm at? 57 is a D. What D is it? What's my main energy level for the D? What energy level am I on? 6, but D is what? N minus 1, so I'm on the what Ds? 5 Ds. So, I have 1 5D. I have 1 5D because I hit 57 before I hit 58. Where's 58? Where's 58? The F block down at the bottom, right? Okay, what is F? F is equal to N minus 2. Well, what N am I at? I'm still at 6, right? What's 6 minus 2? 4. So these are the 4 Fs. And I'm going to fill all 14 of those. So now where am I at? What element, what number? What element, what number am I at now? I'm at lithium element number 71. What comes after 71? 72. So I'm jumping back up where? What block? Back up to the 5D block. Now, tantalum is element number 73. So I come back to the 5D. I have 2 more. So how many total do I have on the 5D? 1, 2, 3. Is it the third one over in the D block? Yes. Now, if you go and you add up all of the little exponents, what should the number be? 73. All right? It should be 73. Let's see. We got 10. We got 20. 36. 38. 48. 54. 56. 57. Okay. 61, 71, 72, 73. Is that what I said it should be? 73? Okay. Add them up to check your work to see where you are at. Okay. Now the next one. Palladium. What I want you to do is I want you to find palladium and give it a shot to see if you can write the configuration. Okay? Here's another one I want you to do. Here's another one I want you to do. Curium. Okay? Curium. Where's it at? Anybody found it? 58. I spelled it wrong, didn't I? All right. I'm going to have to change that here real quick. So you go ahead and do cerium, and I'll change my spelling up there. Yeah. All right. My bad. 96 is where we're rolling to. 96. Down at the bottom. This is a biggie. If you can do this one, you got this jazz. Okay? If you can do this one, you got this jazz here, folks. Go ahead and work it, and we'll go over this probably after the break. All right, curium. We've got element number, what, 96. Okay? So follow along with me. 1s2. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Now remember, here's the point. 6s2, then I have to go 5d1. Then comes 4f14. Then back to the rest of the d's, so that's going to be 5d9. 6p6. 7s2. 6d1, and then 5p, 1, 2, 3, 4, 5, 6, 7. 5f7. What did I say? P? Yeah, 5f7. Okay? 5f7. Now, where's the tough part? Remembering that 1d comes before you can go to the f, right? Did you get that part? Okay? Did you get that part? That's the tough part. All right. I don't know if I have another one here or not. Okay. I do not. So those are the only ones we're going to work. Now, some of the things I've got to tell you. This stuff, okay? This stuff is for WebAssign. This is how you have to do things on your WebAssigns when we're dealing with electron configurations. Okay? A noble gas notation. This is the lazy man's way of writing electron configurations. Okay? You've seen there's a bit of redundancy, isn't it? We always start 1s2, 2s2, 2p6, 3s2, 3p6. Okay? There's redundancy with all of these. Now, in the lazy man's game, the noble gas configuration, here is bromine. Okay? The electron configuration for bromine is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Now, the lazy man's way, the noble gas notation. What is the noble gas before bromium? Not after, before. Well, first of all, I guess we should say, where are the noble gases? Okay? They are column 18, the very last column are the noble gases. So what is the noble gas before bromine? Argon, right? Okay? The one before bromine is argon. So the way we would write the noble gas configuration is we would put brackets around argon, and that would signify that we're already at number 18. And then we just move on after 18. Okay, so this little bracket, argon, right here, that little bracket for argon represents all of those things right there. Does that make sense? So, if they say to write the noble gas configuration, you put the noble gas in brackets and work from there. Now, you're going to see transition metals, okay? And something to make yourself aware of. Look on your periodic table. On your periodic table, they have actual electron configurations on it, doesn't it? See where I'm at? Find the electron configuration on your periodic table. It's there. It's there. But you know what I got to warn you about? Your periodic table does not follow all of the 3 rules. Okay? It does not have the energy levels in increasing order. Okay? We know that there's an overlap. The overlap isn't always represented. So, do not, you can get hints off of that electron configuration, okay? But it's not right based on the way we are teaching it here. So do not just write the electron configuration there that's given on the table. Not correct, okay? Now, if you look at copper, okay? If you look at copper, and on copper's electron configuration, you can see that it says 3d10 4s1. Okay? So as I'm looking at this right here, okay, before I go to the 3Ds, I have to fill up my 4s's. But that's not the case here with copper. Copper is what we call a transition metal. And what that means is this electron, there is electron that is jumping back and forth between the s and the d orbitals. Those energy levels are so close that it's transitioning back and forth. So when we see this 4s1, 3d10 there, we say, oh, that's a transition metal. That element is transitioning. You need to write it as so. Find another element in the D block that is transitioning like that. You got one, Lewis? Chromium. Let's look at chromium. It says 1, 2, 3, 4, 3d5, 4s1. Is that right? My eyes are getting kind of bad. Okay? So we can see that since it's only the 4s1 and 3d5, that element is transitioning. That electron is transitioning. Okay? Do you understand how to tell whether that's a transition element? Because you're going to have to write those transition elements like that with the 4s1, 3d10. Outer and inner energy levels. Okay? Outer and inner energy levels. The key part about the noble gases. Okay? The noble gases, and look up on my periodic table up here. Here are the noble gases, right? The part about the noble gases, that is where the energy level gets filled, a full energy level. Notice that all of these noble gases, other than helium, all of these noble gases are going to be P6. Okay? P6. So as I look, other than the first energy level, okay, here's the first energy level. It ends in S2. But all the other ones are going to end where there's a P6. Okay? Where there's a P6. Where there's a P6. Do I have a P6 here? Not yet, so that's not filled. So how many full energy levels would I have in this element? 1, 2, 3, 4, 5 full energy levels. Now, the one that is not full is what we call the valence electrons. So here is a non-filled energy level. That is the outer energy level. That is what we call the valence energy level. So these would be referred to as the valence electrons. Okay. So where are energy levels filled up at? Where are they filled up at? The noble gases, they're going to be the P6. P6. Now, we've dealt with this before, okay? We've dealt with this before, but just a quick check, okay? And you're going to need this on WebAssign. How do I calculate the number of orbitals? Well, the number of orbitals that you should have is square of n. So I'm on the 5th energy level, all right? The 5th energy level. What's 5 squared? 25. So the 5th energy level will have 25 orbitals. Okay? Now, how many electrons will be on those? Well, each orbital holds how many electrons? 2. Well, what's 25 times 2? 50. So there'll be 50 electrons on the 5th energy level. Okay? What about the 3rd energy level? How many orbitals on the 3rd energy level? How many? What's 3 squared? 9, right? What's 9 times 2? 18. So I have 9 orbitals and I have 18 electrons on the 3rd energy level. Okay? Now, the best way